In this video, we'll talk about how to find a basis for the column space of a matrix. Before we begin, an important remark to make is that when we row reduce, the row operations that we do not affect the relationships between the columns. Let's look at a quick example. So consider this matrix A with entries 1, 2, 4, 5, 2, 4, 5, 7, 3, 6, 6, 9. Now there are some relationships between the columns of this matrix. For example, the second column, which I'll call C2, is twice the first column, which I'll call C1. Also, you may notice that the fourth column, C4, is the sum of the first column and the third column. So C4 is the sum of the first column, C1, plus the third column, which I'll call C3. Let's perform some of our row operations. For example, I can do a row swap. If I swap row 1 and row 2, I would end up with the matrix 2, 4, 5, 7, 1, 2, 4, 5, and 3, 6, 6, 9. And what you'll notice is that our relationships still hold. Column 2 is still twice the first column. And column 4 is still the sum of the first column and the third column. Let's try another row operation. Let's do row scaling. For example, I can do 3 times row 1. This would give me 3, 6, 12, 15, 2, 4, 5, 7, 3, 6, 6, 9. Again, let's revisit our relationships. Column 2 is now 6, 4, 6, and we notice that it's still twice the first column, 3, 2, 3. So that works. Our fourth column, C4, is 15, 7, 9, and we can see it's the sum of the first and the third column. 3 plus 12 is 15. 2 plus 5 is 7, 3 plus 6 is 9. So both of those relationships still hold. Lastly, we can look at our third row operation, replacement. Let's do row 3 minus 2 row 1. This gives me the matrix 1, 2, 4, 5, 2, 4, 5, 7, and lastly 1, 2, negative 2, and negative 1. And again, let's check our relationships. Column 2 is still twice the first column. Column 4 is still the sum of the first column and the third column. So as we've stated in our remark, row operations do not affect the relationships between the columns of a matrix. Now, to find a basis for the column space of a matrix, we do the following. First, we row reduce our matrix. Then we identify the pivot columns of A. Remember, the pivot columns are the columns with leading entries. Lastly, the column vectors of A corresponding to the pivot columns form a basis for the column space of A. These vectors are the ones that will be linearly independent, and all other columns can be written as a linear combination of those pivot columns. So let's try to find the basis for the column space of the matrix above. In general, we know that the column space of a matrix is equal to the span of the columns of that matrix. So in this case, the column space of A is the span of 1, 2, 3, 2, 4, 6, 4, 5, 6, and 5, 7, 9. We know that these vectors are linearly dependent because we have some relationships between the columns. So let's try to go through the process and see which of the vectors I really need. When we row reduce A, we get the following matrix. 1, 2, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0. So my pivot columns are column 1 and column 3, because those are the columns with leading entries. Now, when we have our matrix in reduced row echelon form, it's very easy to tell the relationships between the columns. Looking at the first two columns, I have the first column is 1, 0, 0, and the second column is 2, 0, 0. It's easy now to tell that the second column is twice the first column. And let's look at the last column. The last column is 1, 1, 0. We can easily tell it's the sum of the first column and the third column. We can also tell that the first column and the third column are linearly independent, because the first column is like the standard basis vector E1, and the third column is like the standard basis vector E3. So because I have these relationships in the reduced row echelon form of the matrix, I know these relationships also hold in our original matrix A. Since the second and the fourth column are linear combinations of the first and the third column, I can remove them from our list by applying the spanning set theorem. So in the end, a basis for the column space of A consists of the pivot columns of A, and that is the vector 1, 2, 3, and the vector 4, 5, and 6. One important remark to make is that the basis comes from the original matrix, not the reduced row echelon form of the matrix. A common mistake that I see is that people say the basis is 1, 0, 0 and 0, 1, 0, but that would be incorrect. You need to go back to your original matrix and pick out the first and the third column. So now let's look at some more examples. So for our examples, we want to find a basis for the column space of A. In our first example, we have the matrix A with entries 1, 2, 7, negative 2, 3, 0, and negative 1, 1, negative 1. Now, before we do any calculations, we know that the column space of A can be written as the span of the columns of A. So it can be written as 1, negative 2, negative 1, 2, 3, 1, and 7, 0, negative 1. Now, if these vectors were linearly independent, then this would form a basis for my column space. But we don't know whether or not there are relationships between the columns. We'll have to row reduce A to find out. So again, our first step is to row reduce A. So I'm not going to go through the details, but when you row reduce A, you get 1, 0, 3, 0, 1, 2, 0, 0, 0. So here our pivot columns are the first column and the second column. In the reduced row echelon form of this matrix, the pivot columns themselves are linearly independent because they're not multiples of each other. The third column, however, we can see is a combination of the first and the second column. Specifically, the third column is 3 times the first column plus 2 times the second column. So that tells me that in my original matrix A, I have the same relationship. The vector 7, 0, negative 1 is 3 times the first vector 1, negative 2, negative 1 plus 2 times the second vector 2, 3, 1. Now because I can write the third vector as a linear combination of the first and the second vector, by the spanning set theorem I can remove this from my list. So the remaining two columns are my pivot columns, so I can say that the basis is the set 1, negative 2, negative 1 and 2, 3, 1. And again, I want to take the pivot columns from the original matrix A. I don't want to use the columns from the row reduced version. Do one last example. So in this example, we have the matrix B with entries 1, 0, negative 3, 1, 3, negative 1, 1, 5, 0, negative 5, and 0, 2, 4, 1, negative 6. This time, I'm not even going to write that the column space of B is equal to the span of the columns. I can jump right into row reducing B, and when I do that, I get the matrix 1, 0, negative 3, 0, 1, 0, 1, 2, 0, negative 4, and 0, 0, 0, 1, 2. Once I have the row reduced version, I can identify the pivot columns. That's column 1, 2, and 4. These are my pivot columns. And so a basis for the column space of B will consist of columns 1, 2, and 4. That is the set 1, negative 1, 0, 0, 1, 2, and 1, 0, 1. I know these vectors are linearly independent because they are linearly independent in the row-reduced version of my matrix B. Column 3 was removed from our list because it's dependent on the first two columns. Specifically, negative 3 times the first column plus 2 times the second column gives me column 3. And the last column, column 5, was removed from our list because it is 1 times the first column minus 4 times the second column plus 2 times the fourth column. So by following the steps laid out for finding a basis for the column space of a matrix, we are essentially applying the spanning set theorem by removing the columns that are written as a linear combination of the others and keeping the columns that are linearly independent. So that's it for this video. Thanks for watching.